But hey, everyone, thank you for coming. This has been a podcast that we've been trying to get off the ground for a very, very long time. I am very excited that we got some time finally, some breathing room to start actually talking about our very area of expertise. We're nerds at heart, and we always wanted to talk about blockchain and tech across the space. We've seen a lot of podcasts that have tried to do this. Frankly, not too well, mostly because of just generally a lack of background knowledge in a lot of things. There's things move so fast, it's kind of hard to keep track of. But we always thought, hey, when we ever get some time, it would be fantastic to actually talk about all the incredible things that we're doing at Ava Labs and how it pertains to Avalanche consensus to the greater masses. So this is kind of like the first attempt at that. Whether it becomes a series or not, stay tuned for more on that. But at least we kind of kick it off, and hopefully we'll bring in other people from other ecosystems. With that, all that said, I'm Kevin, and I am a COO at Ava Labs. Been with the project for a very long time. I was one of the people that worked on the core protocol for Avalanche as it was based on a DAG, and then involved in the evolution into a linear chain and so on. And now I do a lot of Twitter trolling, but also a lot of engineering talk in the back end. So that's me.
Awesome. Thanks, Kevin. Yeah, we'll do quick intros and then jump into it. Goon's here as well. Goon, you want to introduce yourself real quick?
Sure. Hi, everyone. I'm Emin. I was a professor at Cornell since 2001 and had worked on peer-to-peer systems in various different settings. Built a system called Karma in 2002, 2003, published in 03, that had proof of work minting in it. I believe it's the first such system that was implemented. And I worked then on finding and characterizing Bitcoin's security, Bitcoin's consensus protocol security, worked on looking at scaling in blockchains, looked at quantifying decentralization in blockchains, looked at securing coins at rest, looked at and built the world's fastest layer 2 protocol, still is the fastest, and called out the DAO hack before it happened, partially at least. And then most recently have been working on fast, scalable, cheap, awesome systems. And that's what got me here.
Awesome. Amazing. Thanks, Goon. Patrick, you want to go ahead and introduce yourself?
Yeah, happy to. I don't have as fun of a story as these guys. I was a crypto engineer at Coinbase for about 2 years. While I was there, I worked on a bunch of different protocols and the integration into Coinbase. I got really deep into abstractions of integrating different chains into the same backend and spent a lot of time on a project called Rosetta there. After getting deep with Rosetta and working with a bunch of different teams, I really decided it was time to dig deeper into a single protocol, and had heard great things about Avalanche, and then this crew here, everyone else that's speaking today, let me join in on the fun as part of this original crew, and it's been a blast ever since. And I forgot to add there, I'm the vice president of engineering here at Ava Labs.
Awesome. Thanks, Patrick. Welcome. Excited to have you. Ted, you want to go next?
Sure. So I'm Ted. I just graduated from Cornell, got my PhD, and Goon was my advisor, and also we worked on the Avalanche project, and that's also like part of my final dissertation. It's very fun, and Kevin was my collaborator on the project. I also worked on the VMware project when I had my intern back in 2018, and that went for a year long and finally became a protocol that's used by Facebook Libra. Now it's called DM Project. And I've been part of the company since day minus 300 or even more. And I'm also one of the co-founders, and I worked closely with Stephen, to make this thing happen, to translate the tech terms and algorithms into the actual product.
Awesome. Thanks, Ted. Welcome. Glad to have you. And then Stephen, why don't you go last?
Hey, thanks. So my name is Stephen Buttolph. I started working on the project way in the early days. I think pretty much after the paper released on IPFS, I was reading that over the summer and was getting really interested in it. So as soon as I got back to Cornell, I asked Goon if I could do research with him, and he asked me to basically hop on and help out implementing a client in Golang. And so I've basically been working with the company ever since as kind of the squad lead and like the lead maintainer of Avalanche Go. So I don't have quite the litany of experience with different projects as Goon, but I've definitely had a lot of fun digging in really deep on the consensus, peer-to-peer, cryptography, databases, etc. side of Avalanche. So yeah, that's me.
Awesome. Well, we're excited to have you all here. So I'm going to kick it over to Kevin, and I'll let you guys take it away.
Cool. All right. So let's get started. So heads up to everybody here. As I alluded to, this is going to be probably a pretty technical podcast. It fills a gap that I frankly have seen for basically every single other podcast in the crypto space. There are other quote unquote technical ones, but they are very superficial and they don't seem to at least typically the hosts are not the world's expert at this, and that creates a bit of a gap, which is totally fine. But we hope to at least fill it up, at least with this starting series, the Metastable series. So there are so many topics to cover. There's so many things that are going on, but I think the best place to maybe start, and we'll use that as a stepping stone to discuss all the crazy engineering going on and core consensus work that we're doing at Avalanche. With Avalanche Go, maybe we start off with the most recent major upgrade that happened, being Snowman++, and then work our way back from there and going forwards into what we're going to see with Avalanche V2 and so on. I have a litany of topics. I'm sure we're not going to get through any of them in high detail, but at least we'll try to. I want to cover Snowman++, MEV in Avalanche, Avalanche V2 at a high level. I want to talk about decentralization, slashing, L2s, governance, so much, but definitely not on this single series here. It'll be a much longer one. So let's get started with Snowman++. Why is Snowman++ there? What is the purpose? And maybe we can kick it off to Steven on talking about that.
Yeah, so Snowman++ is really a major change in kind of how we propose blocks, and it's kind of one of the things that we've been working on with an eye towards improving throughput, latency, and keeping the requirements low for validators from a hardware side. So Snowman++ at its roots is a contention reduction system. So the goal of it is to avoid doing quote unquote like useless work. So originally what could happen is we could have, say, multiple proposers issuing a block at the same time on, say, the C chain. And what ends up happening with that is the network then needs to take time, not just to confirm one of the blocks, but to actually choose kind of which one to confirm. With the introduction of Snowman++, it makes it not impossible, but significantly less likely that there's going to be conflicting blocks at the same height, which allows the network to just focus on confirming things rapidly. And so it ends up, lowering our latencies, so improving our time to finality measurements, while actually improving throughput because we get to do less work, and still kind of maintaining our decentralized first mindset by still involving all of our over 1,000 validators to rapidly achieve consensus. So that's kind of Snowman++ at a high level. Yeah.
So this brings up a good point that I want to ask in a second. But before I go on, all the other speakers feel free to jump in at any time and interrupt with any points you have. I've heard a question that was asked, I think, by Zaki at some point on Twitter. What happens if the proposer equivocates? And this is something that seems to always confuse people because they're typically thinking about consensus, voting-based consensus, proof-of-stake consensus, in terms of classical versions. You have a leader, the leader proposes, collects votes. If there's a quorum, great. If there's no quorum, changes the votes around, shuffles around to whatever new value it wants. Why does how does Avalanche differ there? How does Snowman plus plus differ there?
So let me take this one. Classical consensus protocols have a bunch of different things, have a bunch of things that they do very differently from Avalanche. One of the main things they do is they try to reduce communication by having the followers or other replicas in the system, in the quorum, just accept whatever the leader is telling them. And this puts the leader in a funny position in that its equivocation can cause all sorts of problems. So these protocols then have to make sure that the leader is not equivocating. And equivocation by the lead, but equivocation, by the way, it's a fancy term. It just means the leader says two conflicting things. It says X happened and then Y happened. And both X and Y cannot happen at the same time, but the system has to choose one of them. The leader should never be doing such a thing in classical systems. And therefore, when that is detected, it's actually a major problem for them. And then we get into all kinds of discussion that at some point perhaps we can touch upon about slashing the leader, about taking the leader out of the set, etc., because it's clearly being faulty or perhaps even malicious if it's proposing two different things at the same time. In Avalanche, with Snowman++, the added optimization is done so nicely that if the designated proposer ends up equivocating, it's simply the code simply goes into the slightly longer path of having to choose between two different things in the network. And it's no different from regular Snowman at that point. So we know that that's a code path that works already very well. And the system simply takes a little longer to confirm because it's got more work to do. It's got two different things that are competing for the same slot. And in the cases where the leader is correct and doesn't do that, then the number of rounds to finality is much shorter because, after all, the leader was correct, there is no contention, and therefore the system can do less work to approve the same, outcome. I hope that was clear. And the outcome here is essentially the takeaway message is equivocation by the designated proposer here is absolutely no problem at all.
Right. I think the confusion typically comes along from the fact that in a classical consensus protocol, well, let's take something very concrete. Let's take, for example, Tendermint. It's a very clean protocol, very easy to understand. Suppose that you do not, that you have a leader, or rather, before we even go there, suppose you have a proposer. And the proposer somehow equivocates by creating two conflicting blocks at the same height. It proposes them at the same height, and there is no quorum because the network is split in half, right? So half the network says block hash A, half the network says block hash B, and there is no quorum. The quorum required in Tendermint is 2/3 plus 1. This is where a leader is necessary for something like Tendermint because you require now to effectively switch the leader in a view change mechanism and say, okay, look, this leader equivocated clearly. We're going to now find a new leader because we can't reach consensus. That new leader is then going to propose a new value that has, in fact, a 2/3 plus 1 votes, and then we're going to make a movement forward. That last part about the leader requiring the network to go into a quorum state is precisely where a traditional consensus protocol like Tendermint would differ from Avalanche. Avalanche doesn't require that function from any node in the system. It can do this by itself, and it does this effectively by this randomized process of metastable process of randomized sampling. It samples nodes at random, and then it starts toppling over slowly with some error towards a majority. Now, if the majority is already pretty high to begin with, that toppling is very, very fast. So Avalanche gets to confirmation extremely quickly. If there is a lot of equivocations, that's precisely where Snowman++ comes along and jumps in to effectively reduce that contention and say, look, we'll still finalize these transactions regardless, whether or not a leader equivocates without ever switching the leader or the proposer. But in order to get to confirmation even faster, we'll make sure that somebody proposes a non-equivocating block so we can finalize even faster. And that's like the really the fundamental difference between Avalanche finality and something like Tendermint finality. So I don't know if I missed anything here. Somebody wants to jump in.
So yeah, Kevin, that was a lot of words there. The way I think of Snowman plus plus is that the participants have a slight preference in each slot for a designated proposer. So when you have that, what happens is normally, let's say, I don't know how many people are on this call, but suppose we were all on the call, and I don't know, let's say there's 200 people here, or however, whatever the number is. It's a large number actually.
600.
So 600. Okay, so 600 people. Normally, any one of us could propose a block for any slot, any height, and if we do, then the system has to choose between the 600 of us. But with Snowman plus plus, we all say, look, we're going to so for this height, we're going to have Stephen take the lead, and if Stephen proposes a block, we have a preference for it. So what that means is we're all biased towards that particular choice by that designated proposer, and so that creates that toppling effect that Kevin is referring to. The correct ones among us will adopt what Stephen is proposing, so there will be a supermajority of the people backing the block that Stephen proposed at that height, and then therefore it's going to be very quick to reach the finality we desire. And then for the next height, maybe it's Ted's turn, and we all have a preference for Ted's proposal, and so forth. And that's the process that allows everybody to back behind the same coherent outcome. Otherwise, in a universe with lots and lots of proposers, the system has to do extra work to come up with just one outcome. I hope that's clear. So, Patrick, did you have something to add?
Yeah, the outside of the validator resource efficiency of not doing the useless work, Stephen mentioned around this. One of the most exciting things to me about how this is implemented is really this core VM abstraction that we use throughout the Avalanche Go code base. So Snowman++ is actually implemented as a VM that wraps other VMs instead of its own standalone engine component or something like that. And because of the way that it works, we think it is a first step at an interesting showcase of all the, I guess, general extensibility of the VMs you can create on top of Avalanche. And we've talked a lot about some of the exciting features we want to bring into the subnet landscape. But the primary of these is our proving ground is really the primary network, given that Core ETH and the C chain is really implemented as a generic VM, on top of the general primary network. And so every time we work on improvements for how Core ETH is handled or how we build these VMs, it just prepares us for this, what we hope to be a really exciting explosion of growth around this whole subnet concept and community created VMs. And so in particular, if you have a VM you want to create and you want to send specific consensus messages to other nodes, that's an extension we offer within the VM interface. If you want to change, how you're storing certain data, that's available to you, as opposed to, some sort of kitty cut, basic little binary you can drop in. You have pretty much full bandwidth to really express your creativity within the framework of this VM interface.
So if we're talking about what gets us excited, so yes, I'm always excited about the modularity of the code, but I'm also excited about the MEV reduction. So Kevin, I'll leave it up to you to decide when to bring it up.
Yeah, I have a lot of things here, but maybe. So I mean, immediately after Snowman++, I want to talk a little bit about MEV, but let me actually jump back to MEV later, as it sachets well into Avalanche V2 stuff, and harp on the stuff that Patrick was just talking about with subnets. It is not a topic that I want to necessarily talk about here on this session, but maybe it is an exciting one because there's so many possibilities to be done for subnets, and people haven't really built them up, primarily because there's still not the full set of tooling that is necessary to build cross subnet communication. You can kind of do it in a janky way right now, but it's not there yet. But once it's there, I expect a lot of really interesting subnet developments to happen. So maybe I want to ask the question of what are some really interesting subnet experiments that you guys are excited about. I have obviously one, a proof of work based one. I can explain in a second, but I wanted to leave it open to the rest of you guys to maybe talk about some really exciting subnet experiments.
So maybe I should add some structure to this, a tiny bit of it. So there are two things you can do with a subnet. One, you can introduce a new VM. So that's one direction. And the second thing you can do is you can select your nodes to be different. You have a different set of validators for your VM. So let's maybe delve into both, and you can do both at the same time as well. So there are lots of exciting VMs I can imagine running. The EVM, I hate to say this, but if you look at it critically from the point of view of a system implementer, as we all had to do when we were porting the EVM to work on Avalanche, the EVM choices are far from the ones that I would make to build a fast system. And there are lots and lots of suboptimal things going on at the VM level there. And a better approach, a faster version of this is entirely possible. And for example, I mean, there have been attempts to have a WASM VM. In fact, we also have in the lab a prototype WASM VM that we haven't made public yet. And I don't know that WASM is really all that much better than the EVM actually, but the universe of the virtual machines is enormously large, and so I can imagine much faster, much better versions of virtual machines that would make a couple of things much better. So I mentioned performance would be better if designed properly. The crypto primitives, etc., that are built into the VM could be much better. Zero knowledge stuff built into the VM could be much better, and give us anonymous smart contract execution, for example, and a whole other variety of things could be differently done. So the other thing that's different, that's exciting to me, is the construction of subnets that are location specific. So I imagine subnets that are to be used for, say, US people. And this might seem kind of weird to a crypto native audience, but if you talk to Wall Street guys, this is what they want, right? This is exactly what they want. They want some kind of a thing where they can say, look, we're not going to be trading with, Iran and North Korea because we're contractually obliged to not do that, and we cannot do that on these public networks. So that we want to create our own walled garden, and then you find them going off into funny directions, where they fork Ethereum entirely and they start doing their own specific thing that doesn't interoperate. Instead, I would love to have them as a subnet on top of us. And I can go on like this. I'm not going to. All sorts of VMs are possible where the fee structure and the staking structure, what you have to stake, is different from the default. You may not have to stake just a Vox, for example, but also other things. You may end up having different fee consideration. That is not just you pay per transaction. There are many other things that are possible here.
Patrick, I know you're especially excited.
Yeah, I really think of these subnets as a proving ground for a lot of the interesting, crypto cyberpunk concepts that I think take usually a longer time to develop, because you have to build this entire framework around the VM or abstractions you want to employ. I think a perfect example of this is if you look at Zcash. A lot of the original code was based off a fork of Bitcoin itself, like the networking layer, some of the storage layer and everything like that. And then they could had the freedom to change some parts of the transaction and how that structure works to add some sort of privacy component to it via ZK and everything around there. Now, let's say that you could do that in a much more scalable way, where in the general case, you don't really have to worry about forking some large code base that you have to port in security updates into, or worry about the upstream performance implications of everything you're doing, or even some of the licensing considerations in some cases now. Instead, you can just say, hey, I really want to play around with the idea of having these zero knowledge driven state transitions. Well, go ahead, do that. You can do them with I don't know, outside of the concept of just the ZK proof itself, 100 to 200 lines of code, not have to worry about any of the networking, not have to worry about any of the storage. As a blockchain experimenter, I can't think of something that's more exciting. You want to modify the EVM to drop some of the constraints around tri-E construction to optimize, I don't know, state processing time or state execution time. like go ahead. Like you can take the core ETH, fork it, run it, compile a binary and run it as a subnet, see if it sticks. And I think what we'll see with subnets in many cases is people trying crazy stuff that is really just too complicated to try in other areas. And what will happen is some of them will just kind of, I think, get really popular just because they're so interesting. And we'll see like some of these mini communities form around them. In many cases, I don't think people will just, I don't know, take us off the shelf EVM and run it. I think they'll try something interesting, and then because of that interesting, they can try it out without really impacting the stability of the primary network. I get really excited about this.
I know, me too. Is it fair? Is it fair to maybe say that that the subnet construction is like a universe of many feature specific or VM specific, fully customizable L2s that all kind of talk to the main primary subnet?
Well, I mean, the way I think of an L2 is like you derive your security from a different L1. And in this case, they're really like a proper L1. Like the security itself comes from the validators that make up the validator set that chooses to participate in that subnet. So like I don't think it really, the thing you get is like it's your own blockchain doing your own stuff, but you can communicate more closely with the other subnets that are around. So we built this bridge, this SGX enabled bridge, and it's a beast in terms of its complexity and like everything that's going on with it. The performance and the easy UX a lot of people see doesn't just happen. It takes years and years of research of very complicated topics to turn into something that is as clean and straightforward as we think that the bridge is now. Imagine having to do that for every single subnet and creating thousands of these different types of bridges. Like most of the hacks we've seen over the last year have in some way been bridge related, and it's a very relieving, I think, as a blockchain creator to not have to worry about that. Like, there's this other really popular subnet, and I'm in the Avalanche ecosystem. It's trivial for me to move some sort of data between my blockchain and this other blockchain. I don't know if that answered your question.
No, it's fascinating. No, I mean it's a debate that I don't think anybody's ever going to win on Twitter over like what is an L1, L2. It seems to be blurred. I think obviously the truth here is that the Avalanche network is a collection of all these feature-specific VM pluggable, customizable validator set L1s that all interoperate. Well, right now they don't interoperate easily. Eventually they will interoperate. And it's incredibly exciting to see people experiment with all these different custom features without impacting the primary subnet performance. It's kind of like an isolated sandbox that are live. It's like a million different Kusamas, if the analogy here goes, and all different features and functionalities. It's really cool. Steven and Ted, I don't know if you guys wanted to bring anything.
Yeah, no. Let me just jump in there before we drift off of the topic. Another way to view the subnet construction is to view them as different shards. So functionally distinct things are happening on the different shards we've got. We've got the AVM on one side, and we've got the EVM on the other side. And one of them is designed for one use case, which is value transfer and asset digitization. The other one is designed for smart contracts, and there could be many, many others. And so you're getting a glimpse of what it's like to be in a sharded universe. And the subnets are exactly like shards. You can have as many of them as you like. What you would like to do to get ultimate performance is to group together those things that are functionally related. Now, when other people use the word sharding, they typically are referring to a more random assignment of contracts to different sets of nodes, which I have cautioned them about, and I've cautioned, I'll say it again publicly. That style of traditional sharding, where users or contracts or load is distributed across the set of resources you've got in a random fashion, then you get all sorts of problems in a universe like a blockchain, because everybody will want to be in with the popular crowd. And the game theory then says, well, once you shard, you're going to have, before the sharding, you had one chain, one problem. After sharding, now you have K chains and K+1 problems, because everybody wants to be on the popular one. That problem did not go away. You just created K minus one other problems for yourself. Plus, you got the problem of inter-shard communication. But with subnets, it's different. You've got this functional grouping. You've got people who are functionally related wanting to be together. and things that are functionally distinct could be on separate ones. And yeah, and I can go on and on like this, but yeah, so you can view them as L1s, L2s, or you can view them as shards. They are their own thing, and I think the community hasn't really explored them sufficiently yet. I don't think the system has given people enough tools yet, but we're working on that. But I'm really excited about what can come of them.
Yeah, no, I think just kind of touching back on the kind of like customizability of our VMs. I think a lot of people interacting with Avalanche probably thinks that the C chain is basically it, because that's kind of such a primary part of our network, and it's certainly where a lot of the DeFi and a lot of the activity is. And I think it's really amazing and kind of worth thinking about that the C chain is a fully generic plugin that it's not integral to any like Avalabs, or it's not critical to like the Avalanche Go core system. And so really it kind of showcases the flexibility of that architecture and like how complicated slash like useful and efficient something can be implemented as. So I think really just that is a great showcase for the flexibility, and I'm really looking forward to, as kind of some of the other people have mentioned, like ZK VMs and other like more complicated cryptographic things, because I think it's an amazing kind of playground for it. But yeah, I think that's just kind of something that I'm always amazed by on the tech side.
Yeah, so following Stephen's topics, yes, indeed. So it's a common, misunderstanding quoted, or, some confusion that people just think, oh, you Ava X, your Avalanche platform is only about C chain, it's a smart contract chain. How does your project compare to project A, B, C? All the others also do Ethereum compatible chains. I think they missed a very important point that Stephen pointed out. So to be honest, the funny thing or the irony here is we spent perhaps 90% of our effort during our early stage of development not on the C chain, but on its fundamental consensus engine. So what we plan to do is just like we want to build something as a service. So we want to build a consensus engine. We have the Snowball consensus. We also have Snowman, linearized kind of structure. We have all these engines in place. Then we think about, so since we have all these cool consensus mechanisms and the engines in place, and for any VM, it's just a matter of supporting fully ordered transactions. So it doesn't make a lot difference when it comes to implementing either EVM or WASM or anything else. That's why we had our initial ideas of designing such plugins, or even it could be sandbox in the future. So it's like if you do a comparison, instead of thinking about L1, L2, other projects, I think it's better to think of it in terms of traditional cloud computing, because we know on AWS you can just easily spawn your own virtual machines. You don't have to care about how that virtual machine is migrated among different hardware machines or actual computers in the data center. So we are doing a similar thing here, but in the blockchain, in terms of blockchain, the blockchain world. So we have a decentralized platform, and we have our engines. And as a showcase, we developed C chain, and that's it. So it's kind of interesting. So if you know about the development history, C chain is just like showing off. And we have the ability, it's about the potential of the engine. And for sure, for subnets and for, customizable VMs, anyone can develop their own plugins, just like our C chain. And our C chain may serve as a well demonstration for that purpose.
Yeah, I fully expect at some point, once the tooling becomes super mature, it is very nascent, it's very complicated right now. But once it becomes easy, I fully expect somebody to kind of pioneer a few VMs on different subnets, and then for there to be like infinitely many copycats of them, but of all different slight changes. Like there might be a subnet which copies the entire set of addresses from Ethereum over into a new C chain, and then it's kind of like the Ethereum quote unquote old ideas. or there might be like a BTC subnet where you just copy all the BTC addresses over to the subnet, and that becomes effectively green BTC. Like there, it's UTXO based, as fast as you can possibly get. It has all the features of Bitcoin, and yet it's green. It doesn't melt the polar caps. So yeah, I'm very excited, but there's so many topics. So maybe I want to jump into a different set of topics. And I've heard many times us get questioned or get some eyebrows on Twitter around this idea of slashing. Why does Avalanche get away with not having slashing? I know I'm going to trigger a few people here because we always roll our eyes that slashing is just not necessary. It solves for problems that don't really exist. There are ways to effectively get what you want with basic things. But I wanted to open up the floor here to the rest of the crew and talk a little bit about why slashing doesn't matter. Maybe Gun, do you want to start off?
Yeah, let me just say where this idea came from. So look, it's well understood by now that everybody in this space just kind of got their start in Bitcoin. They don't know about, like, for them, history starts with Satoshi Nakamoto and there's nothing before them, okay? And most of them are essentially trying to recreate what Bitcoin did. And so it's sort of like reasoning, the reasoning kind of goes like this. Well, to have some kind of to have some kind of truth, some kind of a shared data structure that everybody agrees on, there should be some cost or penalty associated with creating or trying to create an alternative truth. Otherwise, what would keep people from doing that? And how would you be able to tell? And so that's sort of the beginning of this conversation. And once you lock into that frame of thought, then you kind of go, well, yeah, how would I know? If I'm given, normally with proof of work, if I'm given the longest chain, I just latch onto the longest chain. But if I'm given, five different EVM chains, 5 different Ethereum chains with Ethereum 2 chains, how would I know which one's the official one? And so, well, there should be some kind of cost. And so that you buy into that frame, and you find yourself having to design these really complicated slashing procedures. And the bottom line is there are many systems out there that don't have slashing in them, and yet they work just fine. They work absolutely fine. Bitcoin doesn't have slashing. If you create an alternative block, yeah, you lost some opportunity cost maybe, but you don't actually lose your coins on the original chain. There's no slashing in Bitcoin. It works just fine. So anyway, I just want to stop there. I can rant on this topic for hours, and I can get triggered pretty.
Yes, I know.
So, prior to getting triggered, let me simply say that there already exist chains, especially the one that you're trying to copy, already doesn't have slashing in it. It's just that you talked yourself into thinking that it's a necessity, and now you're trying to figure out what's happening. And there are many other things that are more nuanced about, what do you slash, et cetera, But maybe I'll end up with this. Here's my prediction. All of these slashing-based chains, not prediction, statement. All of these slashing-based chains are risks for everybody who participate in them, because you can actually lose your principal due to slashing. That's just a big risk you take. And then here's my prediction. The biggest source of slashing will not be malicious attacks, because nobody in their right mind would launch a malicious attack that is curable by slashing. To be cured by slashing, I have to be below the threshold where my attack would damage you. So, well, then I would never do that. What would I do? Well, I would wait until I'm large enough to actually cause damage. So instead, the prediction is slashing will end up taking more honest people's money due to software and hardware errors and network configuration errors than anything else on that system. So we'll live and see what happens. My predictions usually come true. So let's give it a few years and see what, see people deploy some slashing-based systems and check out what happens. It already did happen on Cosmos. And I'm very, very eager to see it happen on these networks where people are loudest about slashing.
Steven, I don't know if you have any thoughts here.
Yeah, no, I think I don't really have too much to say. I think that really one thing to point out is just that in these consensus systems, going back to kind of the literature on consensus, these consensus mechanisms are fault masking consensus mechanisms. So you can have some mechanisms that attempt to detect Byzantine faults and kind of roll back when a Byzantine fault happens and repair the state of the network. But most, consensus systems that are implemented today are what they call like masking of faults. So essentially, it doesn't matter if there's someone being Byzantine in the network. It just ignores them and moves on with like an honest majority or an honest supermajority. So these systems are kind of designed so that a like small enough Byzantine actor doesn't matter. And as Goon kind of alluded to, if your Byzantine actor is too large past that point, slashing doesn't actually buy you anything. Slashing will not be able to kind of fix your chain if you have like a major attack. So kind of at the end of the day, the question is the risk imposed on your good users that you don't want them to be concerned about their money, is that risk imposed on them worth whatever you think you might be getting against an attacker? So that's kind of
yeah. And there is other ways to employ. Like we always get asked, well, what's the incentive for validators on Avalanche to never misbehave or never be offline, whatever, never do anything wrong? Well, if you're offline for a certain amount of time, you don't get your reward. That's already one form of slashing. It's effectively kind of like working on a random fork on Bitcoin. If you're just working on a random fork, you're just never going to get your reward. And if there is like game theoretic arguments here that are extremely powerful and more than sufficient. If you're working to create misbehavior in the system without having enough voting power, all you're doing is slowing down the network, and you're not buying yourself anything. So you would only do anything valuable to yourself somehow if you got big enough, in which case you could cause safety issues. But in that case, you're creating a disaster scenario for your own system that you have stake locked up yourself. So the game theory simply does not work out. It works out to null for anybody doing anything malicious here, and slash it seems like simply something unnecessary on top. But maybe I don't know, Ted. Also, before I move on, do you have anything about slashing?
I think slashing, it's really hard to prove anything about it. Time will tell, as you mentioned. But my belief is in alignment with our teams. It's like slashing. If you do it, it's whether you do it or not. It's mostly based on your belief of how malicious or how the overall network behaves. And I mean, it's a good assumption to it's just like in our legal system. We do not try to convict someone of some crime before we have the evidence. And even so, we do have very conservative way to get him or her punished. Same for slashing. So I don't think it's a very healthy thing for people to do slashing in such a system.
So there was obviously a big recent issue that happened with Solana and a liveness thing. And it brings up a really good topical conversation that seems to be missing significantly on crypto Twitter. Maybe intentionally or not intentionally, doesn't matter, but we should probably talk about it. And that happens to be the liveness guarantees of a proof of stake system versus a proof of work system. And there's a lot of misconceptions there. People think that Bitcoin will chug along, doesn't matter how much of the network goes down, it always keeps going. And obviously, the big misconception there is that it will keep going in a very unsafe way, in a way that could easily revert all your transactions. So I wanted to open up the floor. Maybe we'll start off with Patrick, and give us an overview of what the misconception here over liveness between the different protocols are, and what should a protocol really prioritize for.
Yeah, sure. I mean, generally, I think of liveness as, in many ways, like the heartbeat of the system. And in some proof of stake protocols, like the rewards basically distributed to different validators depends on their participation on chain in some sort of block. So if you have, I think particularly in the case of Solana, for example, like the blocks contain transactions of basically a validator's view of the world. So they'll include like what their preference is as a state root, or like the accepted frontier, or wherever they think is a valid block. And other networks, will do some sort of like aggregated signature approach where they'll take, at each block, like everyone will send their, their signature into some leader. The leader will put that into a block, or just not even aggregate it, really just throw all the signatures into a block and in some sort of header or something like that. In those systems, right, like this kind of ties back into the slashing discussion. If you're not participating in that way, you're going to be slashed for not being up for some period of time. And chains makes various decisions around how aggressive to be around that. In some cases, you're given a few hours of buffer room so you can perform upgrades or whatever you want to do, migrate your infrastructure or something like that. In other chains, you're given a few minutes. And so in the case where there's network instability and like the chain that continues survives, you could be penalized for doing something like that, or not participating, maybe not of any of your own fault. But liveness for most integrators is really only one component of it, maybe sometimes the smallest, right? Like if there's millions of dollars at play, safety is the only thing that matters, and you'll stop far before there's any consideration that you could potentially commit a safety failure. And Avalanche nodes have not to be too specific, but like have various configuration options that let you as an integrator determine or parameterize your own view of how you want to proceed with the liveness versus safety trade-off. So if you say, I really only want to accept transactions that are really universally considered, valid. There's no contention whatsoever. There's no disagreement, and 99.9% of the network agrees. And I want my probability of a double spend in like some sort of Byzantine adversary case to be, 10 zeros, 0.0000, whatever, to the one or something like that. You can do so, but at the cost of liveness, because you'll be trying to pull the network to the nth degree to understand what its true view of the world is. But I think what you'll see is if the stake and reward component or slashing component isn't really tied to the uptime, I think in many ways sometimes the ideal situation to avoid like overloading a system that may already be overloaded, if there's a gap between liveness and the finalized tip, in many cases is just to wait for stability to return before you continue to accept blocks or try to accept blocks again. Especially if you're an integrator, but in many cases, like if there's, let's say, a partition of AWS's data centers and like a bunch of people are running validators on there, you may want to wait to continue producing blocks for a little bit before you start overloading the network with all sorts of gossips and whatever partitions result as part of that provider downtime or something along those lines.
Steven, any thoughts from you?
Yeah, I mean, I think that Patrick kind of really nailed it with, I think most people are concerned about losing money. Crypto is not a very forgiving place. If you send a wire transfer using a traditional banking system, there are protections in place so that if something goes wrong, someone screws something up, you aren't just going to lose your money. Crypto, if you send a transaction that you're not expecting, you're going to end up kind of getting wrecked. And so I think that really it's important to design the entire system from like a safety first perspective. People don't want to lose money. We've definitely heard horror stories about various exchanges getting kind of wrecked by some reorg that happens. I think especially I think Ethereum Classic is probably the famous example that's happened recently, but or not super recently, but that's kind of the worst case scenario, and it really ends up driving people away from your platform. So I think guaranteeing that people aren't going to just lose like huge amounts of money is really key to adoption. And so, when you're developing these kind of liveness first systems, you're really making that trade-off. Yeah, I think it's a scary practice for the users. So, yeah.
Ted, anything you want to say?
Yeah, so I think that question, the original question, was very interesting. So let me take a more academic point of view. So to us, like to researchers, usually we don't categorize consensus with proof of work or proof of stake, because it's a really ill-defined kind of term, because people believe that proof of something is the core consensus mechanism, which isn't the case. It's a quite a consensus among researchers who are doing related research topics. So the thing here is when people really mean when they say proof of work, they really mean the Nakamoto consensus or the Bitcoin Ethereum kind, where proof of work is required to do mining. Whereas for proof of stake, what they're really getting at is not proof of stake itself, because we are not using money or stakes to make consensus, but we use it to do admission, like defend against cyber attack, things like that. But instead, usually proof of stake consensus protocols, they use quorum-based consensus, votes, 2f plus 1, 3f plus 1, all the votes, classical kind. So for that category, usually you have different models, and when people say they're concerned about the liveness there, it's more about the network model instead of proof of work versus proof of stake. And the reason that some people may think, oh, Bitcoin has better liveness, compared to proof of stake systems, is simply because Bitcoin is, due to its the way it works, it's fully synchronous. So you can imagine it's block by block, and you have a block time, an expected block time that's roughly at some 10 minutes or so, and it cannot be too long or too short. And the reason that it cannot be too short is because it takes time to disseminate the block. Otherwise, the blockchain won't converge. So it's part of the consensus. So it has to do that one block after another, has to wait for enough of a time. Usually in academia, it's called the delta, like the maximum network delay, or the time for something to be propagated throughout the network. And whereas for POS protocols, they use very different, algorithms, but they mostly either have quorums or, like us, it's like probabilistic quorums or samples. So for these vote-based protocols, they can be synchronous, partially synchronous, or asynchronous. And it sounds, kind of really, really academic kind of terms. But in short, synchronous protocol is like we still make assumption on how long the message can be delivered, or how long the maximum time it takes to deliver something. And whereas for asynchronous protocols, fully asynchronous one, they don't make such assumption. They just hope for some randomization and somewhat they converge. And our protocol, has some traits from the asynchronous world, because we are also randomized, but we're not strictly synchronous. So we are weaker, we use weaker model in that, meaning we are more robust in the given network condition. So I don't know what kind of exact algorithm Solana uses, so hard to make comment there. But usually, if you really want to look into the liveness, it's more about how the protocol decides and the network model it uses. It doesn't have much to do with either proof of work or proof of stake, because these are for admission control.
Yeah, there's a lot of really subtle things there. Go ahead.
There are a lot of things to say there. So let me just give everybody, like, these guys are really brilliant, and they're all kind of experts at their fields and various different aspects of distributed systems. So they use a lot of jargon. Let me make it simpler for people. So safety is like riding a bike and not falling off of it, and liveness is like making progress. And what do you want? Well, you want to not fall off your bike because you'll get banged up, and you want to make progress. So that's great. When you have a protocol like, proof of work protocol, what you're really doing is, you're able to stay on the bike even when the network is in a bad state. Suppose half the miners cannot communicate with the other half of the miners. Well, what's going to happen? both sides will make progress. That's great. That's kind of like, you know what that's like? That's like making progress on your bike in circles. You feel that wind in your face. That feels great. Lord, I know how awesome it is when I'm on the bike and, going fast and the wind is in my face, but you're going in circles. You're not really making progress. And those two halves of the network, when the network heals, there's going to be a problem. And you're going to discard one of the two chains that got created. And the way people actually measure time to finality on proof of work chains is they have a little meter connected to the wheel. And when the wheel has spun that many times, they say, okay, this is final. Well, if you start going in circles like an idiot when the network is in a bad state, yeah, you will build blocks. People will think they're final. And then when the network heals, they're going to discard things that were considered final. That's really, really, really awful. That's like falling off your bike. It's the equivalent of falling off your bike. So in your effort to keep wind in your hair, you ended up doing something really, really terrible and ended up falling off the bike in the end. So that's that whole argument. I just, I don't want to be normative and say this is better than that. But the facts kind of speak for themselves that when there's high value involved, you want to do things where nobody ever thinks that anything is final. Essentially, you want to be able to fail safe when the network is in a bad situation. You don't want to just keep on going for the sake of feeling that wind on your face. So anyway, I know we're going to be running late. We're going to end at 9:03, I believe. So I'm gonna cut it short here, and Kevin, let you ask another question, maybe a final question or something in the last minutes.
Yeah, there is way too much to cover here, but let's maybe just kind of ask a high-level question here on, the next couple of months. What is exciting to each and every one of you as far as Avalanche development goes? Maybe we'll kick it off with Patrick.
Naturally, I'm biased because I'm the one that helps decide this. I think the subnet excitement speaks for itself. When I look for opportunities for like side projects to do, it's always on top of my mind. But related to subnet feature improvements and performance updates, that's my favorite. I obviously can't give more than one answer, so I'll cut it there.
Steven.
Yeah, so what really got me interested in the space was distributed systems and consensus. And so one thing that I'm really looking forward to is kind of working on and fleshing out the Avalanche V2 spec. So I know we didn't get to talk about it too much here today, but I'm really excited about it, and I'm always excited about other kind of performance-related improvements. So I think those are kind of me my big things that I'm looking forward to rolling out in the next coming updates. So
yeah, Avalanche V2 is a doozy, but as we get closer to it, I'm sure we'll have another one of these sessions. Ted, what about you?
Oh, so for me, it's pretty clear that if one word for the answer is storage. I know there's the consensus topic, or the core engine of any L1 project sounds very compelling. Like, people are really interested in how these protocols work, and they're having a lot of white papers and academic papers about this topic. But I envision, in the future, consensus will no longer be a bottleneck, especially in our system. So on that front, we gradually realize that, first of all, EVM has become the de facto, standard, although there's no such standard. The code, the get code is the actual standard. So people really focus on the DeFi and all the on-chain applications, but that also means there has been a lot of burden on the execution of the virtual machine, and mostly for the storage part, and also how you manage, not only about the hardware storage, like how you manage the data on the storage medium, like SSD, but also how you manage the state. So on that front, it's been part of the research project that we worked on a database called SecretsDB, and I'm very excited about seeing it play an important role, or a role in the Avalanche Go code. And it also in the future some storage optimization, even if you use LevelDB or RocksDB. When we roll out more optimizations and more functionalities on our C chain, there is definitely a lot of chance to do storage-based optimization to speed up bootstrap time and the processing time and make it much easier for everyone to run a full node.
So I guess it's my turn. Yeah, this is what happens, Kevin, when we get all these low-level hackers into the room and ask them, what they're most excited about, and they give you some super geeky answers. And I'm no exception, but and I don't know which one to pick. But okay, let me just go through. Obviously, I'm really excited about the things that are happening at the platform level. I was very excited about Snowman++, very excited about V2. There's cool dApps coming on board. I'm actually excited, very, very excited about what we will be doing with subnets. We will. The goal here is to digitize all of the world's assets. We have the right technology for this. And demonstrations of how to do this, they're just so exciting. ILO is coming on board, new asset types. We're one of the few groups that are thinking about brand new things to bring in to crypto. And so that's really cool. And so I do things on the side that are sort of skunkworks-like or hobby-like, things like privacy-conserving technologies, things like NFTs, computer-generated art, and I'm excited about those. But the thing that I'm really excited about, like the thing that really gets me going in the morning, is the interactions we have in this space. It's the community.